So thank you, Srika, for the kind introduction. And I'm very happy to be back to Bangalore, where I have been 5 years ago in the context of the Mahalanobis Memorial Lecture. And I have wonderful memories of my short stay there. And it's nice to be back, in a sense, through Zoom. So today, indeed, I will talk about, the subject is multivariate quantiles. Multivariate quantiles, and as we shall see, also multivariate ranks, two concepts that go hand in hand. But I will focus on the concept of multivariate quantiles. And now, okay. So the concept of a quantile, of course, is a very fundamental concept in statistics and probability. And there's the population concept of a quantile function, and there's the empirical, the concept of an empirical quantile. And these are fundamental tools in basically all domains of applications of statistics, and also in theoretical statistics. It is fundamental in descriptive statistics. It's fundamental in inferential statistics. And if you think about it, and despite a uninterrupted research activity with the objective of constructing satisfactory concept of multivariate quantiles, where these notions are fully available for univariate real observations only. Only in the univariate case do we have a fully satisfactory definition. And as I mentioned, where the concepts of quantile function and distribution function in the population, or empirical quantiles and ranks in the samples, are intimately related. Basically, a quantile function is the inverse of a distribution function, and an empirical distribution function is nothing but a rank divided by a sample size. So to be precise, I will define quantile. I will insist on the fact that the quantile function should be the inverse of a distribution function, and the empirical distribution function is a rank, but instead of dividing by n, I always will divide by n plus 1. The reason is that then, I'm mapping the observations to the open interval 0, 1, and not to the closed interval. Now, we have then that the population quantile of order tau, where tau is somewhere between 0 and 1, is the collection of points x in the space of the random variable for which the distribution function is equal to tau. And the empirical quantile of order tau is the collection of observations with rank equal to n plus 1 times tau. Later on, when we deal with multivariate observations, we will have quantile contours instead of point valued quantiles, and empirical quantiles contours, and the definition will be the same. Now, as I mentioned, the concept of quantile and distribution functions and their empirical counterparts, ranks and signs, are well understood in dimension 1. And since they are well understood in dimension 1, this is the point we should start from when thinking about extending to multivariate situations or more complicated distributions on manifolds, for instance. So in the univariate case, let me report some very basic and elementary facts. So I will deal. Hello?
Just a small note that so by rank, you mean basically the ordered observations.
Exactly. So the smallest observation has rank 1, the second smallest rank 2, etc., and the largest has rank n. Okay.
And clearly, it makes sense only in the real.
And it only makes sense well, as an immediate definition, yes, it only makes sense in the univariate real situation. And our objective here will be to extend this to a multivariate situation, right? Which is the challenge. So,
sorry to interrupt again, but can I ask a question as well?
Yeah, of course you can.
Right. So, sorry, I'm not very familiar with this field, but is it the following that there's a probability distribution from where I have samples, and these samples are some real numbers, and I'm arranging them in an order, and this is what the ranking is. And of course, so now you have the distribution function, which tells me what is the probability of something being below a certain threshold. And the quantile function is just the inverse of it. So it will take values within. Okay. Thank you.
Yes, and the empirical distribution function computed at an observation is the rank of that observation divided by n, but I prefer dividing by n plus 1 for as you will see why. So we are back to the univariate case, the case where we have a clear picture of the problem. And of course, I will denote by Z a Lebesgue absolutely continuous random variable, and I will assume that it has non-vanishing density. This is not really necessary, but it makes life much simpler. Then the classical distribution function, f sub p, is a mapping from R to the open interval 0, 1, and the value at the point Z is the probability to the left-hand side of Z. This is the very elementary definition, and the quantile function Q sub P is just the inverse of that distribution function, mapping 0, 1 to the real. So here you have a picture. If you have this mapping FP here from Z to FPZ, well, obviously it is mapping, because it is monotone increasing, it is mapping this half line here to this segment here, and the probability of this half line here is the same as the probability of this segment here. Now, what are the main properties of that distribution function? Well, f is monotone increasing. That's something very important. And I insist that keep in the back of your mind that a monotone increasing function is the derivative, hence the gradient, of a convex function, okay? Because it is monotone increasing, it has a well-defined inverse, so the quantile function is well-defined. It is also monotone increasing, and hence it is also the gradient of a convex function. Okay. Second property is distribution freeness, and this is extremely important. If you have that Z has distribution P, then the distribution function Fp computed at Z is a random variable, which is uniform over the interval 0, 1. This is the fact that the distribution function is a probability integral transformation. As a consequence of this, when you look at the quantile function and you look at the probability of the half line from -infinity to Q computed at some point U, well, this probability is the probability of this segment here, of this interval, and this probability is, since it's uniform, this probability is U. So that Q computed at Q qualifies as the quantile of order U of P. Now we will borrow from measure transportation a very convenient notation, and we will say that F is pushing P forward to the uniform over 0, 1. This is the notation which is used in the theory of measure transportation, and it just means that if Z has distribution P, then Fp computed at Z has distribution U. So you have your Z here, you map Z to the unit interval by using the distribution function f sub p, and you obtain something which is a uniform over this interval 0, 1. Similarly, you have that Q is pushing the uniform 0, 1 forward to the original distribution P. So you should view this F and this Q as mapping a distribution to another distribution. Okay. And finally, and this is not an unimportant, it's not a detail, we have that because of that, precisely, F completely characterizes P and Q completely characterizes P as well. So these are properties of the univariate, the traditional univariate distribution functions and quantile functions that that are the reason for the inferential the fact that these two tools are important inferential tools, and these are the main properties we would like to see in a multivariate extension of these concepts. Another vocabulary detail is that this transform from Z to FZ is the univariate version of the copula transform. So you are transforming your random variable into a uniform over 0, 1 random variable, and in dimension 1, this is the copula transform, which of course will be interesting mostly in a multivariate setting. I don't know why this doesn't work. I have to. Now, I insist that the distribution freeness and monotonicity properties of F are absolutely essential here, because they are the properties that entail the fact that the probability content of a quantile region, in this case, a half line from -infinity to the quantile of order U, this probability only depends on U. And because the distribution of FPZ is uniform, moreover, it only depends on U, it is equal to U. If this distribution freeness property would not be there, you would not have a control over the probability content of your quantile region. I mean, if you would not have this distribution freeness, you could define a median, for instance, and that median could, for some distribution, have probability 1/2 on each side, which is what we would like to see. But for some other distribution, it could have 0.4, 0.6, still for some other 0.3, 0.7, etc. And a median with such properties, you wouldn't like to call a median, right? So it's this distribution freeness property of the distribution function that provides the fact that the median has always probability 1/2, 1/2 on each side.
So by distribution freeness, you just mean absolute continuity of the density?
No. I mean that the distribution of F computed at Z does not depend on the distribution of Z, which is P, okay? For any P, F sub P computed at Z it has the same distribution, which in this case is the uniform over the unit. And that is very important, because when you are inverting the distribution function to obtain the quantile function, you obtain control over the probability content of the regions you are creating with your quantiles. And if you don't have that control, then it's not a quantile. I mean, the quantile should be a quantile of order tau, and this tau should be the probability to the left-hand side of the quantile, irrespective of the underlying P. This is very important.
So in other words, I can also say that we have found an invariant of for a class of for distribution function. So I have found a function, when composed with any random variable, I get the same distribution.
Yes, provided that you also transform the distribution function. So
Yeah,
it's a
indeed.
kind of invariance that if you change the distribution of z and you change the distribution function, and then these two changes compensate each
Cancel
other.
out, yeah, cons cancel out each other.
Okay. So these are the very important properties of univariate distribution and quantile function. Now let us go to dimension 2 and higher. And of course, we have a traditional definition of a distribution function, which extends the univariate definition. And this definition we all had in our elementary probability classes. And if we have a bivariate z now, z1, z2, with distribution p, absolutely continuous, etc., then the classical definition of this bivariate distribution function computed at z1, z2 is actually the probability that the marginal variables z1 is less than z1, the marginal variable z2 is less than z2. And this is the same as the probability that the copula transforms f1 z1, f2 z2 of the random vector capital Z. This is the same thing as the distribution function of this copula transform computed at this point. Let me show you a picture. So here is the observation space, and here is the unit square. And the distribution function is mapping one point here, this point Z here, to a point which is here. And the distribution function computed at this point Z is the probability of this region here, which is actually the distribution function of the copula transform of Z computed at the image of Z1, Z2. So these two probabilities here are equal. Now, what are the properties of this concept? Well, the problems are obvious that if you look at this distribution function computed at Z1, Z2, which is this, it is not uniform over the unit square. Here we have that the marginals are uniform over the unit intervals, but the joint distribution is the copula, and the copula depends on the original distribution P. So the distribution freeness property is not there. It is only there in the marginal sense, okay? And as a consequence, if you look at the probability contents of the region obtained by inverting this distribution function, this traditional distribution function, this probability content is not distribution free, and it will depend on the underlying P. And so it's a bad concept for a quantile. So the traditional bivariate distribution function and its inverse do not qualify in the sense that they do not enjoy the property we're expecting as distribution and quantile functions.
Can I clarify something? Sorry?
If you may.
I had another question. In the first bullet point, did you mean uniform over 0, 1 squared? Just to clarify, so it's written the interval 0, 1, so I was a little confused.
Yeah, it's a typo. It is not uniform over 0, 1 square. It's the unit square here. Okay.
I see.
So,
okay.
So you don't have this distribution freeness property that makes the definition of a quantile a satisfactory definition. So you have marginal distribution freeness, but not joint distribution freeness. Okay.
And if Z1 and Z2 were independent, then you would have probably gotten
Yes, of course, but that one's two independent. That's a collection of two univariate situations. Okay.
Okay.
So also note that a very bad behavior of these definitions, if you are rotating your unit square, for instance, you have completely. It behaves in a horrible way. It's not very satisfactory. And the blame goes to the copula transform, which fails to achieve distribution freeness. Okay, so using the copulas in order to create multivariate quantile regions probably will not lead to any satisfactory solution. Now, this has been noticed a long time ago, and it has motivated an alternative approach, which is the concept of depth. But before going to the concept of statistical depth, let me introduce the idea that instead of an ordering, as we have in the univariate case, from left to right, from minus infinity to plus infinity, once you get to dimension 2, there is no left and there is no right anymore. There are central points and there are as many infinite points at infinity as directions in the plane. So no minus infinity plus infinity, but an infinite collection of infinities and a central region. And therefore, instead of an ordering from left to right, we should think of an ordering which goes center outward from a central region, median, for instance, to infinity in all directions. Okay. So let us have a new look at the univariate case, but from a center outward perspective. And let us define something I denote as f plus minus. And this is just 2 times f minus 1. And this 2 times f minus 1 now has values in minus 1, 1, which is the unit ball, the open unit ball in R, right? And obviously, f plus minus contains the same information as f. And now it is a measure of centrality or inlineness. Because if f plus minus at z is close to 0, it means that z is close to the median. If it is close to minus 1, it means that z is far away on the left-hand side. And if it's close to plus 1, it means that z is far away to the right-hand side. And call this f plus minus the center outward distribution function of P. Obviously, it is also monotone increasing, so it also has a well-defined inverse. And this inverse we call the center outward quantile function of P. What are the properties of this center outward distribution function and quantile function? Well, they are monotone increasing because 2 times f minus 1 is monotone increasing if f is monotone increasing. And hence, they also are gradients of convex functions. Both are gradients of convex functions. Obviously, also, if you look at f plus minus computed at z, where z has distribution p, well, this is still uniform, but now it is uniform over minus 1, 1 over the unit ball. So you have your distribution freeness property, and f plus minus is still can be called a probability integral transformation. In the notation of measure transportation, you have that f plus minus is pushing the underlying distribution p forward to the uniform over the unit ball. And q is pushing the uniform forward to the distribution p of z. And both fully characterize the underlying distribution p. So this center outward concept satisfies all the properties we are expecting from a distribution function and its inverse as a quantile function. Here is a picture, and here is what it means. So you have here your f plus minus, which is 2 times f minus 1. Well, it's the property of this interval here that leaves to the left-hand side and to the right-hand side the same probability. If z is to the left-hand side of the median, that probability is fz here, and then you have fz here. And here you have something which is the absolute value of f plus minus. If z is to the right-hand side, then well, it's the same story, but now it's the distribution function to the left and the right-hand side here are just computed at z prime, which is this point here that leaves the same probability to the left as z has to the right. So the absolute value of f plus minus is the probability of a central region, which is here, and defines equal tails on both sides. Okay. So you have that this f plus minus decomposes into an absolute value, which is the probability of contact of that central quantile region, and a unit vector, which is which we denote as s plus minus, which has values either -1 or +1, so values on the unit sphere in R, and that is a sign. Okay, and that absolute value is uniform over 0, 1. The sign is uniform over the two values -1 and 1. That is, it is uniform over the unit sphere in R, and they are mutually independent. Okay. Now, this uniform over -1, 1 actually is the spherical uniform, which we denote here in dimension 1 as U1. So the spherical uniform over the unit ball, meaning that it is the product of a uniform over 0, 1 and a uniform over the sign, which is either +1 or -1. This will be important when we go to higher dimension. So here is the picture again. The sign here could be -1 or +1. When it is -1, you have this central region here and the two tails, which are f computed at z. And when it is +1, you have the same central region here, but now the tail is the distribution function computed at this z prime here, which is if z has here to the right-hand side a given probability, this guy z prime here has the same probability to the left-hand side. Now, if you look at this absolute value here, well, it also can be written as 1 minus 2 times the minimum between fz and 1 minus fz. And for those of you who know the definition of the Tukey depth, well, this is exactly, this quantity, this minimum here is exactly the Tukey depth computed at z in the univariate case. So the center outward distribution function and the Tukey depth function are intimately related, and they coincide up to a simple linear transformation. And of course, as we have shown, the center outward distribution function satisfies all the properties we're expecting from a distribution function. And therefore, both the Tukey depth and the center outward distribution function do the job of defining central quantile regions of given order tau. That is, the central region here will have probability content tau, irrespective of the underlying distribution P. So they do the job. And so there's a hope that Tukey depth will provide an admissible or satisfactory concept of quantiles. Also, when you go to higher dimension 2, 3, etc. So let us look at this center outward approach and this Tukey depth approach in dimension D, strictly larger than 1 now. Because in dimension 1, we don't need that. We have the traditional definition, which is okay. Now, Tukey depth, of course, was introduced for higher dimensions.
Sorry, Marc.
Yes?
So by depth, you basically mean another way of defining a rank.
No, not exactly. I will provide the exact definition in arbitrary dimension in a moment. So let us look at a random vector now, a random vector Z, with this distribution function absolutely continuous with respect to Lebesgue, and now we are in RD. Okay, then this is the definition of depth. The depth of a point Z in RD is the minimum over all possible hyperplanes running through Z of the probability that is left above the hyperplane. So a picture will be easier to interpret. So let us look at this point Z1 here. And let us look at all the hyperplanes running to Z1. And for each hyperplane, let us compute the probability of the region which lies above the hyperplane. Okay? One of these hyperplanes, so I have many of them, and one of these hyperplanes yields a minimum for that probability. Well, that minimum is called the depth of Z1. Okay, so if that minimum is very small, that means that Z1 is not deep into the distribution. It is close to, it is far away from the center. When this depth is large, well, it means that the point is deep inside the distribution. Now, you can compute this for all points Z1, Z2, etc. And you can collect all the points Z's for which the depth has the same some given value delta. This provides you with a contour, which we call the depth contour. Okay, well, such a contour has been proposed as a concept of a quantile contour. And that's the motivation for this theory of statistical depth that goes back to Tukey, and there have been several other definitions of several other concepts of depth, but they all have the same properties or the same weaknesses. So question, does this region here, which is the inner part, the region which is inside the contour of points with given depth, the delta, does such a region qualify as a central quantile region? If we, in the sense of the properties we have seen before. That means, can we consider that such a region qualifies as a central quantile region? Well, the problem is that, again, the depth is not distribution free. I mean, if you compute the depth at a random point Z with distribution P, well, that very much depends on P. It is not distribution free. And because of that, the probability contents of a depth region also very much depends on the underlying distribution P. And therefore, it does not qualify as a quantile region. You have no control over the probability contents of such a region. So the answer to the question is no, it is not it does not qualify as a quantile region. And by the way, depth functions in general do not characterize the underlying distribution. There's a nice proof of that in a recent paper by a Czech guy, Nagy, which appeared recently. You also have that depth regions are necessarily convex, even if you have a distribution which is highly non-convex. I mean, if you have a banana-shaped distribution, you would expect that the quantile regions also have the shape of a banana. This is not the case with depths. The depth regions always are convex by construction. So this is not the right way to define multivariate quantiles. They do not satisfy. They do generalize the univariate concept because in dimension 1, they do the job, but as soon as you go into dimension 2 and higher, they no longer qualify as a satisfactory extension. Now, there are other ways to extend the univariate concept, and maybe these other ways will be better. And that's how we will meet the ideas of measure transportation. So recall that this F plus minus and also its inverse Q plus minus, the center outward distribution and quantile functions in dimension 1, which were doing the job, were gradients of convex functions, that is monotone increasing mappings between R, the observation space, and the open unit ball, S1. Okay, and you had this push forward property that F is pushing P forward to the uniform over the unit ball, and Q is pushing the uniform over the unit ball forward to the underlying distribution P. Well, let us now denote by U sub D the spherical uniform over the unit ball as D in dimension D. Right? So that's the product of a uniform for the distance to the center and a uniform for the directions. So you have a uniform over the unit sphere for the signs. And there's a very famous theorem by Robert McCann, goes back to 1995 or 98, which tells us that if you have that Z is Lebesgue absolutely continuous over RD, then there exists an almost unique gradient of convex function F, such that F is pushing P forward to this uniform over the unit ball. So one of the characterization of the univariate center outward distribution function is that it is pushing, it is a gradient of convex function, pushing the distribution P of Z forward to the uniform over the unit ball in R. Well, that definition, we can, without any change, we can extend to arbitrary dimension D, and let us define a center outward distribution function in RD as this unique gradient of a convex function pushing P forward to the uniform, the spherical uniform over the unit ball in RD. So that will be, that suggests, this is the definition that we will take for our center outward distribution functions now in dimension 2 and higher. It's another way of extending the univariate case. Okay. And now let us check whether the properties we are expecting are satisfied. Okay.
Marc,
so again, yes.
Yeah, so just to refresh, so the spherical uniform by that distribution, spherical uniform distribution, you mean basically the product of the radial times the directions, right?
Yes, right. So you have something which the density only depends on the distance to the center, and that distance to the center is uniform over 0, 1. Okay. So here is the definition. Now we call center outward distribution function of P the almost everywhere unique gradient of convex function pushing P forward to the spherical uniform over the unit ball in RD. Question, is that a good definition? Is it appropriate? Does it satisfy the properties we're expecting from a distribution and quantile function? Well, the answer is yes, because by construction, F plus minus is quote unquote monotone increasing in the sense of being the gradient of a convex function. Being the gradient of a convex function is a form of multivariate monotonicity. Yes.
Just one more question. Hello, can you hear me?
Yeah, I do.
Yeah. I'm sorry for interrupting so many times. So right in the beginning, you had mentioned that your distributions are fully supported. So that basically means that your mappings, that is a quantile function and also the distribution function, they are both very well defined. They are all gradients of the convex function. So therefore monotones, strictly monotone. Whereas if the distribution is compactly supported, then this will not be monotone.
So the definitions are simple when the distributions are absolutely continuous and have non-vanishing densities, meaning that the densities are bounded from below and from above over any compact sets. This can be relaxed. And I have a paper with Spanish colleagues on that relaxation, but I will not take this into account here because it just makes the definition a little bit more complicated. So I go for the simple situation.
Sure.
So
thank you.
Being the gradient of a convex function is a form of multivariate monotonicity. Second, by construction, FPZ is uniform of the unit ball, so distribution freeness is there. Okay, because of this, it has been shown by what's his name? The guy who got a field medal recently.
Villani.
Not Villani, the next one, another Italian name.
Alessio.
Yes, Alessio Figali. Alessio Figali has shown that F plus minus is a homeomorphism. And because it's a homeomorphism, its inverse is well defined. And so you have that Q is well defined. It is also a gradient of a convex function, etc. So all those properties here are satisfied. And so now, if you look into the unit ball, well, with the uniform over the unit ball, the natural central quantile regions are the nested spheres with radius tau, tau in between 0 and 1. And the probability contents of a sphere with radius tau in this uniform distribution over the unit ball, that probability content is precisely tau. And so when you take the image by this sphere of radius tau using the center outward quantile function Q plus minus, you obtain a closed and connected region because we have a homeomorphism. The probability content of which is the same is also tau. And therefore, this provides us with quantile regions with controlled probability contents, irrespective of the underlying distribution. And finally, those F plus minus and Q plus minus both fully characterize the underlying distribution. Let me show a picture.
So here I have a question.
Yeah. So here is a picture. So here is what we are having. F plus minus is pushing the distribution of the random vector. Here is pushing it forward to the uniform over the unit ball. Uniform over the unit ball means that if you take here the sub-ball with a radius tau, well, the probability contents here is tau. And the inverse image by Q plus minus, which is a homeomorphism of this ball, this sub-ball here, well, is something I'm depicting here. And of course, because this is a transport, the probability content, which is tau here, is also tau here. You are transporting this mass of probability here. You are transporting it here. And so you are obtaining indeed something that qualifies as a quantile region of order tau. And it is, if now tau ranges from 0 to 1, you will have a central point and then a collection of nested contours that are larger and larger with probability tau growing up to 1. And this is the collection of the center outward quantile regions for that distribution P, and it satisfies all the properties we are expecting from a distribution, a quantile function in dimension D. Now, the moot point is that no analytical form, with a few exceptions, no analytical form is possible for F plus minus and Q plus minus. If you have an analytical form for P, give me a density, for instance, computing F plus minus means you should solve nonlinear partial differential equations of the Monge-Ampère type, and this is something nobody can do. So even pure mathematicians working in partial differential equations are looking at numerical solutions. And numerical solutions are what we statisticians would call simulations. Okay. There's an empirical counterpart to these unique gradients of convex functions, etc. I would say a word about it in a moment. And if you compute for large sample values these empirical counterparts, here is what you obtain. So the blue lines here are the image by the quantile function, the center outward quantile function of the hyperspheres center at the origin. Here they are spheres because we are in dimension 2. So if this corresponds to a sphere of probability tau, well, this is the quantile contour of order tau. And then you have the images of the radii, the rays running from the center in the unit ball, and these are those red curves here. And so the probability content of the full region in between two consecutive red lines here is constant. It's the same all over. So this means that here you see the region in between two consecutive red lines. They are sine curves. This region is small, meaning that there's a high concentration of observations here. But here you have that the region is very, very large. You have a big gap between this one and the next one, meaning that that region is basically empty. And that's indeed the fact, because this is dimension 2. We can look at pictures. This is a banana-shaped distribution. Actually, it's a mixture of 3 Gaussians. And you see that, well, these solutions here adapt to the banana shape of the distribution. And actually, we can show, I will probably mention that a little bit later on, we can show that these blue lines will converge to the actual population quantities in a Glivenko-Cantelli way, that is uniformly and almost surely. So, yes. This was the population case. Now let us look at the empirical case. How do we define the empirical quantiles when we are observing a sample Z1, Zn of observations? And again, let us first look at the empirical case in dimension 1, because there we are in a familiar situation. How do we compute the empirical distribution function in dimension 1, the fully classical concept? Well, what we are doing is looking at a map of the observations, Z1, Z2, Zn, to a regular grid of the unit interval. And that regular grid is of the form 1 over n, and I'm taking n+1 in order to remain in the open interval. So it's 1, 2, 3, n over n+1. And so Zi is mapped to the rank of Zi divided by n+1. So what we are doing, we are constructing a monotone increasing mapping of the observations here of the sample to that grid, okay? And we have then the very strong consistency property, which is the Glivenko-Cantelli property, that the max over the sample values between 1 and n, the max of the deviation of this empirical distribution function and the actual one goes to 0 almost surely as n goes to infinity. Well, let us do the same thing with our center outward concept. And let us look now at the grid. Here is the bivariate case, and I'm looking at the regular grid over the unit ball. So I will factorize n into nr times ns, and then there will be a residual n0, say, and I will consider ns points over the unit sphere regularly as possible over the unit sphere, and I will consider nr, a grid of nr points over the radii. And so I will have kind of pizza cooling, how do you call it, grid of this form. And well, in the univariate case, since the mapping here was monotone, it is also minimizing the sum of squared distances between the z and their image Ri over n+1. So this is minimizing the total Euclidean distance between the observations here and their images on the grid. Well, let us do it the same thing here and compute the optimal pairing of the observations which are here with the grid points which are here by minimizing the sum of squared distances between these points and the point they are mapped to in the grid. And here is what we obtain. So we have these nested spheres here, and their image in the sample space are provided here with this code color. And this is what we will call, so this mapping from the observations point here to this grid is what we call the empirical center outward distribution function. And we prove Glivenko-Cantelli result for that empirical center outward distribution function, which has exactly the same form as in dimension 1. Okay, so asymptotically, you do recover the population center outward distribution. And in a sense, this is exactly the same result as the simulation result the pure mathematicians are using to construct their numerical solutions to the Monge-Ampère partial differential equations. This was for RD. Now,
Professor Hallin?
Yeah.
Sorry, will it be, so sort of the time is up, but maybe will it be possible to wrap it up in the next few minutes?
Yes, I will. So it's also possible to extend this to other situations than RD, such as directional data, which take values on hyperspheres, or any other compact manifold, such as a torus. So here I'm skipping details. Here are pictures of what we can do over the sphere. So for directional data, we also can define quantile regions and quantile contours and signs and ranks now over the sphere. Switching to other problems, you all have heard about quantile regression. Quantile regression is something very important and much more informative than traditional conditional mean regression. Now the only concept or the only method for quantile regression that exists so far is about a single output quantile regression, where the output of the regression problem is univariate. And the reason is that there's no sound concept of a multivariate quantile. Now, with this concept we have introduced, we also can do multiple output quantile regression, meaning that we will have quantile regression tubes. So here you have a picture. You have one covariate, which is X, and a bivariate output, which is Y1, Y2. And so when X varies, you have these tubes, the probability contents of which is under control. It's tau, say, if you look at the tube of order tau, and the central, so the intersection between all those tubes is a quantile median regression. It's a median regression, a regression median, excuse me, which is here, this red curve. So this, for applications, is something quite promising and useful. Here are further pictures. Now, since you probably will have the slides, I have here a section on measure transportation in a nutshell, which might be useful for some of you who are not familiar with measure transportation. That goes back to Gaspard Monge and was further studied, and with the main breakthrough was by Leonid Kantorovich during World War II. And I'm also explaining how the result by McCann is appearing in the history of that subject. And this is the most general result we are using here, because who would like to define quantiles and ranks, etc., only for distributions possessing second-order moments? And well, the problem by Monge and Kantorovich is an optimization problem, and the objective function of this optimization problem is a quadratic, in our context, is a quadratic function of the observations. And so if you don't have finite second order moments, this objective function is plus infinity, and there's no optimization possible. So the result by McCann is absolutely fundamental in our approach. Okay, well, as you know, measure transportation has been a very active subject of mathematical analysis. We have these two field medalists in a row, Cedric Villani and Alessio Figali. It has been used in probability with applications in risk measurement, comonotonicity, etc., optimal coupling, and in theoretical economics as well, for the optimal allocation of resources, etc. Statisticians have been much more slower to use measured transportation, but I have no doubt that this type of application, construction of quantile regions will become very popular, because it's the only sound concept of a quantile in dimension 2 and higher available so far. So concluding is that finding an adequate concept of quantile in RD is an important problem. It has been open for more than half a century. It has generated an abundant literature, triggering in particular the development of copulas and statistical depths, but none of these attempts had been successful, and because it does not satisfy the fundamental properties of the univariate concept, which are the properties that make the univariate concept a successful inferential tool. Quite on the contrary, the measured transportation version I have been proposing here does satisfy all those properties, and so it is the first adequate definition of a concept of multivariate quantile available in the literature. This opens the door for countless statistical applications, distribution free rank-based tests, R estimation, also in a multivariate or directional context, multivariate notions of value at risk, expected shortfall, etc., multi-output quantile regression, I showed you some pictures, multivariate growth charts, multivariate Lorentz curves, etc. All those ideas that are based on quantile, on the concept of quantile. Now, some references. Here are references for the theory and the definitions of these center outward distribution and quantile functions. So basically, this paper in 2017 and this one in 2021. Then this is about R estimation and rank tests in dimension 2 and higher. So for Varma models, and also for multiple output regression and MANOVA. And this is for the problem of vector independence, testing the independence, not the non-correlation, the independence between two vectors, not two random variables. This is about directional data. This is about multiple output quantile regression. And I think that's all I can say. And I thank you for your patience, and I apologize if I have been a little bit too long. Thank you.
Thank you very much for the wonderful talk. Let's thank the speaker. So I open the floor for, there have been a lot of questions in between the talk, but I suspect that there'll be more. So please go ahead with your questions.
I'm listening.
Yeah, hello. So when you take the spherical uniform distribution, so there we have the non-smoothness at the origin. So now if
Right.
we choose that to be any other smooth measure, so do we lose much, or I mean, so will the contours, quantile contours and other things will preserve if we change the measure?
Well, if you take the Lebesgue uniform over the unit ball, you will not have this the fact that the signs still will be uniform over the unit sphere, but you will not have the fact that the modulus of f plus minus is uniform over 0, 1. So this is one property of the univariate concept that will be lost. It is not dramatic, but it's nicer to keep it. So, for instance, you would have that the ranks would not be kind of equidistant on the radii anymore. So it would start very slowly and then accumulate as you get close to the unit sphere. So that's why the spherical uniform is preferable, but again, it's not so important probably.
In terms of contour, will the shape or other things will change? I mean,
it will change the labeling of the contours. The contours will not be labeled anymore by the radius of the corresponding ball. There will be a transform there, which will depend on the dimension. So the whole picture will be less simple if you do that. But the collection of contours will remain the same. The labeling will be different.
Okay, so I have one more question. So when you define the empirical quantile and empirical distribution function, so you are taking the regular grid. So
yes.
So as long as the distribution matters, we can take the random grid also. I mean, so we take the random sample, and will that work, or do we have something?
That works, but it's possible to find more regular grids than the IID grid. I did not provide details, but there are methods of construction originating in numerical analysis, because constructing grids in numerical analysis is a daily exercise that are more regular than an IID grid. But IID would be perfect. Actually, any grid which is such that the empirical distribution over the grid converges weakly as n goes to infinity to the spherical uniform, that's fine. So as soon as you have this weak convergence, all the results I have been providing still hold.
Okay, and does the similar result hold for quantile also, like using the quantile? So you have uniform convergence over all sample points for the distribution, but for the quantile, do we still get the uniform, or it is?
What do you mean? Do we still get the uniform?
I mean, so
note that, strictly speaking, the quantile contours are only defined as collections of observations. So you have actually a contour which is a discrete collection, a finite collection of observed points. Now, in the paper with Del Barrio and two other authors published in the Annals of 2021, we provide an interpolation method that creates a continuous contours, so an interpolation of those observation points, which is an interpolation within the class of gradients of convex functions. That's, of course, the challenge here, that you cannot do any interpolation. It has to remain a distribution function, and so it has to or a quantile function. And so we should come up with an interpolation that remains within the class of gradients of convex functions. And then you do have contours that are closed contours, nicely continuous, still satisfying Glivenko-Cantelli.
Yes, no, I am not talking about the interpolation. So in your Glivenko-Cantelli result, you take the maximum over all the sample points. So if we take instead of taking Fn and Fn, I mean theoretical and empirical one. So if we take the quantile for same case like F inverse and Fn inverse, so do you have the same result for maximum?
I'm not sure I understand what you mean. Do you mean that my version of the version I showed of Glivenko-Cantelli is a maximum over I, okay? Whereas the traditional way is a soup over X. Well, that's equivalent in the univariate case, because in the univariate case, you are doing an interpolation, which is an interpolation that traditionally is with a step function. So that's by no means compulsory. I mean, you could take any monotone increasing interpolation and get exactly the same result. There's no information contained in this interpolation. It's just an interpolation, and the step function is just one way of doing it. But for instance, you could take a linear interpolation and have the same Glivenko-Cantelli result, which is equivalent to a max over I Glivenko-Cantelli result. And when we do our interpolation in dimension D by within the class of gradients of convex function, the story is the same, irrespective of the gradient of convex function interpolation you are coming up with. You will have this Glivenko-Cantelli property in a subversion if and if only if you have it over with a max over I form. So it's the same story.
Okay, thank you.
So Shivshankar, if you have further questions, maybe we can come back to it towards the end. Are there any further questions?
Please feel free to download the slides and distribute. I have no objection.
Thank you very much. We will upload them to the website. Shivshankar, sorry that I cut you off. If you have further clarifications, you can go ahead. I'll stop recording, perhaps.